Imagine a cosmic monster, millions or even billions of times more massive than our Sun, lurking at the heart of galaxies, shaping their very existence. This isn't science fiction. These are supermassive black holes, the titans of the universe, the engines that drive galaxy formation and evolution. They're not just voids in space. They're dynamic powerhouses that can spawn stars, influence the fate of entire galaxies, and even connect them through invisible filaments of energy. If you've ever wondered about the true scale and power of these cosmic behemoths, and how they've sculpted the universe as we know it, then you're in for a mind-bending journey. Stick around, because we're about to dive deep into the heart of darkness and emerge with a new understanding of the light. The birth of supermassive black holes. At the heart of nearly every large galaxy, including our own Milky Way, lies a supermassive black hole. These cosmic behemoths are not just notable for their size, but also for their profound influence on the galaxies that host them. They are born from the remnants of massive stars, but their growth is a complex process that involves the accumulation of matter over vast periods. The seeds of these monsters are thought to be either the direct collapse of massive gas clouds or the remnants of the first generation of stars. These seeds then grow by accreting gas and merging with other black holes, eventually reaching masses millions or even billions of times that of our Sun. The scale of supermassive black holes is almost incomprehensible. To put it into perspective, if our Sun were a grain of sand, a supermassive black hole with a mass of 1 billion solar masses would be a large boulder. Their immense gravity warps space-time, creating a region from which not even light can escape, known as the Event Horizon. This gravity also exerts a powerful influence on the surrounding galaxy, shaping its structure and evolution. They act as cosmic engines, driving the formation of stars and galaxies. Their energy output can be so immense that it outshines entire galaxies, making them visible across vast cosmic distances. Supermassive black holes play a crucial role in galaxy formation and evolution. They regulate star formation by heating and expelling gas, thereby controlling the growth of their host galaxies. This process is thought to be responsible for the observed correlation between the mass of a supermassive black hole and the mass of the bulge of its host galaxy. The energy released by the accretion of matter onto the black hole can also trigger powerful jets of plasma that extend thousands of light years into space. These jets can heat the intergalactic medium, preventing gas from cooling and forming stars. This complex interplay between supermassive black holes and their host galaxies is a key area of research in astrophysics. Cosmic titans, size and scale. Supermassive black holes are the colossal engines that power the universe, their immense gravity and energy shaping the very fabric of galaxies. Nestled at the heart of nearly every large galaxy, these cosmic behemoths can weigh anywhere from millions to billions of times the mass of our Sun. To put that into perspective, one supermassive black hole, like the one at the center of the elliptical galaxy Messier 87, has a mass equivalent to 6.5 billion suns. That's a staggering figure, enough to make even the most massive stars in our galaxy look like mere specks of dust. Their size is only part of their story. The power they wield is equally mind-boggling. As matter falls into a supermassive black hole, it forms an accretion disk, a swirling maelstrom of gas and dust that heats up to incredible temperatures, emitting intense radiation. This process can outshine entire galaxies, making these black holes some of the brightest objects in the universe. Quasars, for instance, are incredibly luminous active galactic nuclei powered by supermassive black holes. They can emit thousands of times more energy than a typical galaxy, making them visible across vast cosmic distances. The role of supermassive black holes in galaxy formation and evolution is akin to that of a cosmic architect. Their immense gravity influences the orbits of stars and gas clouds, shaping the structure of their host galaxies. They can trigger star formation by compressing gas clouds, or halt it by blasting out powerful jets of energy that heat and disperse the gas. This dual role makes them crucial players in the life cycle of galaxies. Without them, galaxies might look vastly different, if they could form at all. Their influence is so profound that their presence can determine whether a galaxy becomes a sprawling spiral or a dense elliptical. Consider the Milky Way's own supermassive black hole, Sagittarius A star. It's relatively quiet compared to its more active counterparts, but its presence is still felt. Stars orbit around it at astonishing speeds, their paths tracing the invisible lines of its gravitational pull. This dance of stars provides a cosmic map, allowing astronomers to study the black hole's properties and behavior. Despite its quiet demeanor, Sagittarius A* is a testament to the power and influence of supermassive black holes, a silent titan shaping our galaxy from its very core. The Event Horizon, point of no return. At the heart of every supermassive black hole lies a boundary called the Event Horizon, a point of no return where the gravitational pull becomes so immense that not even light can escape. This boundary isn't a physical barrier but a threshold in spacetime, a cosmic point of no return. To grasp its scale, consider that the event horizon of a supermassive black hole can span millions of miles, dwarfing the size of our Sun. For instance, the event horizon of the black hole at the center of our Milky Way galaxy, known as Sagittarius A*, is roughly 17 times the size of the Sun. This immense scale is a testament to the enormous mass and gravitational influence of these cosmic behemoths. The event horizon marks the boundary where the escape velocity exceeds the speed of light. Escape velocity is the speed needed to break free from a gravitational field. In our solar system, the escape velocity from Earth's surface is about 11.2 kilometers per second. But near a supermassive black hole, this velocity becomes unattainable, even for light. This is why the region within the event horizon is shrouded in darkness, earning black holes their name. The event horizon size is directly proportional to the mass of the black hole, a relationship described by the Schwarzschild radius. The more massive the black hole, the larger its event horizon. Supermassive black holes play a pivotal role in the formation and evolution of galaxies. They act as cosmic engines, driving the dynamics of their host galaxies. The immense gravitational pull of a supermassive black hole can influence the orbits of stars and gas clouds, shaping the structure of the galaxy. For example, the gravitational influence of Sagittarius A* extends far beyond the event horizon, affecting the motion of stars in the galactic center. This influence can lead to the formation of complex structures, such as galactic bars and spiral arms. Additionally, the energy released by matter falling into a supermassive black hole can regulate star formation, preventing galaxies from growing too large too quickly. This regulatory role is crucial for the balanced evolution of galaxies. The event horizon also serves as a cosmic boundary that separates the known from the unknown. Once matter crosses this boundary, it is inevitably drawn towards the singularity at the center of the black hole. The singularity is a point of infinite density where the laws of physics, as we know them, break down. The journey towards the singularity is a one-way trip, as nothing can escape the gravitational pull once it crosses the event horizon. This makes the event horizon a fascinating subject of study for astrophysicists who seek to understand the fundamental nature of spacetime and gravity. The study of supermassive black holes and their event horizons provides valuable insights into the workings of the universe, shedding light on the mysteries of cosmic evolution and the fabric of spacetime. Singularity, the heart of darkness. At the core of every supermassive black hole lies a singularity, a point of infinite density where the known laws of physics break down. This enigmatic heart of darkness is the result of matter being compressed to an unimaginably small volume, creating a gravitational pull so strong that not even light can escape. The singularity is shrouded by the event horizon, a boundary beyond which our understanding of the universe falters. It's a place where time and space become so warped that a single second for an outside observer could equate to an eternity for something falling in. The scale of a supermassive black hole's singularity is mind-boggling. To put it into perspective, consider the Sun. If you were to compress it into a singularity, it would be about 3 kilometers in diameter. Now, scale that up to a supermassive black hole, which can be millions or even billions of times more massive than the Sun. The singularity at the center of the Milky Way, known as Sagittarius A*, is roughly 4 million times the mass of the Sun. Yet, its singularity is still incredibly tiny, a mere 17.9 kilometers in diameter. This immense mass packed into such a small space is what gives supermassive black holes their incredible power and influence over their surroundings. Supermassive black holes play a pivotal role in the formation and evolution of galaxies. They act as cosmic engines, driving the dynamics of their host galaxies. The energy released by the accretion of matter around the singularity can influence star formation, regulate the interstellar medium, and even shape the large-scale structure of the galaxy. In some cases, the energy output can be so immense that it results in active galactic nuclei or quasars, which are among the most luminous objects in the universe. This energy can heat and expel gas from the galaxy, potentially halting star formation and thus regulating the growth of the galaxy. The interplay between a supermassive black hole and its host galaxy is a complex dance of cause and effect. As the black hole feeds on the surrounding matter, it grows in mass, increasing its gravitational influence. This can lead to the formation of galactic bulges, bars, and even influence the overall morphology of the galaxy. Conversely, the galaxy's structure and dynamics can also affect the black hole's growth and activity. For instance, galaxy mergers can funnel large amounts of gas towards the central black hole, triggering intense periods of activity. This coevolution of galaxies and their central supermassive black holes is a fundamental aspect of the universe's structure and evolution. Relativity and spacetime warping. Supermassive black holes, those cosmic behemoths lurking at the hearts of galaxies, are not merely celestial vacuum cleaners. They are dynamic actors, shaping the very fabric of spacetime and orchestrating the evolution of galaxies. Their immense gravity, a consequence of Einstein's theory of general relativity, warps spacetime like a bowling ball dimpling a trampoline. This warping is not a gentle curve but a profound distortion, altering the paths of stars, gas, and even light itself. The scale of this warping is staggering. Near the event horizon of a supermassive black hole, time itself slows down, and the fabric of space is stretched and compressed in ways that defy everyday intuition. Consider the Milky Way's own supermassive black hole, Sagittarius A star. Its mass is about 4 million times that of the Sun, yet it's confined within a region smaller than our solar system. The space-time around it is so warped that light coming from behind it can be bent around, creating a gravitational lens. This effect is not just a curiosity. It's a tool astronomers use to study distant galaxies and the early universe. The warping of space-time also influences the orbits of stars near the galactic center. These stars, like S2, orbit Sagittarius A* at speeds of up to 3% of the speed of light, their paths tracing out rosette-shaped orbits that would make Newton blanch. The power of supermassive black holes extends beyond their immediate vicinity. They can drive galaxy evolution through a process called active galactic nuclei, AGN, feedback. As matter falls into a supermassive black hole, it forms an accretion disk, a swirling maelstrom of superheated gas and dust. This disk is not a passive structure. It's a dynamic, violent place where friction and magnetic fields heat the material to millions of degrees. Some of this material is funneled into the black hole, but some is ejected in powerful jets and winds. These outflows can stretch for thousands of light years, shaping the galaxy's interstellar medium and regulating star formation. In this way, supermassive black holes act as cosmic thermostats, preventing runaway star formation and maintaining a balance that allows galaxies to evolve. The warping of space-time by supermassive black holes also has profound implications for our understanding of the universe. It provides a natural laboratory for testing Einstein's theory of general relativity in extreme conditions. For instance, the Event Horizon telescope's image of the supermassive black hole in M87 revealed a bright ring of emission surrounding a dark central shadow, a direct consequence of space-time warping. This image, and others like it, offer a glimpse into the nature of black holes and the fabric of space-time itself. They challenge our intuitions and push the boundaries of our knowledge, reminding us that the universe is a place of wonder and mystery. Accretion disks, cosmic whirlpools. In the vast expanse of the cosmos, supermassive black holes reign as titans, their immense gravitational pull shaping the very fabric of galaxies. At the heart of these cosmic behemoths lies a phenomenon as awe-inspiring as it is destructive: the accretion disk. This swirling maelstrom of gas, dust, and stellar debris is not merely a spectacle. It is the engine that powers the black hole's growth and influences the evolution of its host galaxy. Picture a cosmic whirlpool, a vortex of matter spiraling inwards, heated to extreme temperatures by friction and gravitational forces. The light emitted from these accretion disks can outshine entire galaxies, making them visible across vast cosmic distances. The scale of these accretion disks is mind-boggling. They can span millions of miles, with some reaching sizes larger than our solar system. The matter within them is compressed and heated to millions of degrees, emitting intense radiation across the electromagnetic spectrum. This radiation is not just a byproduct. It is a testament to the black hole's insatiable appetite. As matter falls into the black hole, it releases energy, a process so efficient that it dwarfs nuclear fusion, the process that powers stars. This energy output can influence star formation, regulate the growth of the galaxy, and even expel matter back into the interstellar medium, shaping the galaxy's structure. The power of these accretion disks is not just theoretical. Observations of active galactic nuclei, the extremely bright centers of some galaxies, provide direct evidence of their influence. These nuclei are powered by supermassive black holes, their accretion disks emitting jets of plasma that extend thousands of light years into space. These jets can heat and disrupt the intergalactic medium, preventing the formation of new stars and regulating the galaxy's growth. In this way, accretion disks are not just passive features. They are active participants in the cosmic dance of galaxy formation and evolution. Moreover, the study of accretion disks offers insights into the very nature of black holes. By observing the light emitted from these disks, astronomers can infer the properties of the black holes themselves, such as their mass and spin. This information is crucial for understanding the role of black holes in the universe. For instance, the spin of a black hole can influence the shape and size of its accretion disk, as well as the energy output of the system. In this way, accretion disks serve as a window into the mysterious world of black holes, revealing their secrets one observation at a time. Jets and outflows, cosmic fireworks. Supermassive black holes, those enigmatic giants lurking at the hearts of galaxies, are not merely passive behemoths. They are dynamic engines, driving colossal jets and outflows that shape the very fabric of the cosmos. These jets, often stretching for thousands of light years, are a spectacle of cosmic proportions. Picture a garden hose, but instead of water, it's a torrent of charged particles, and instead of a backyard, it's the vast expanse of interstellar space. The power behind these jets is staggering, with some packing the punch of a billion suns. The process begins with the accretion disk, a swirling maelstrom of gas and dust that spirals into the black hole. Not all of this material makes it in. Some is ejected at near-light speeds, forming these spectacular jets. The energy involved is mind-boggling. In a single second, these jets can release more energy than the sun will in its entire lifetime. This energy doesn't just vanish into the void. It interacts with the surrounding galaxy, heating gas, triggering star formation, and even sweeping entire star systems out of the way. It's a cosmic ballet of creation and destruction, all orchestrated by the supermassive black hole. The outflows, while less collimated than jets, are no less impressive. They are like cosmic winds, sweeping through the galaxy and shaping its evolution. These outflows can regulate star formation, preventing galaxies from growing too large too quickly. They can also enrich the intergalactic medium with heavy elements, seeding the universe with the building blocks of future stars and planets. In this way, supermassive black holes act as cosmic gardeners, tending to their galactic gardens and ensuring a balance between growth and decay. The scale of these phenomena is hard to comprehend. The jets of the quasar 3C273, for instance, stretch for over 100 light-years, dwarfing the Milky Way itself. The energy output is equally staggering. The black hole at the center of the galaxy, M87, powers jets that outshine the entire galaxy. This energy doesn't just dissipate. It carves vast cavities in the surrounding gas, creating bubbles that can span entire galaxies. These bubbles can suppress star formation, effectively controlling the growth of the galaxy. It's a testament to the immense power and influence of supermassive black holes, the true engines of the universe. Quasars, beacons of the early universe. Quasars are among the most luminous objects in the universe, outshining entire galaxies with their immense energy output. These cosmic beacons are powered by supermassive black holes, which reside at the centers of galaxies. The black hole's gravitational pull draws in surrounding gas and dust, forming an accretion disk. As this material spirals inward, it heats up to incredible temperatures, emitting intense radiation across the electromagnetic spectrum. This process makes quasars visible from vast distances, even when the galaxies hosting them are otherwise too faint to detect. The scale of quasars is mind-boggling. A single quasar can emit energy equivalent to trillions of suns. To put this into perspective, consider that the entire Milky Way galaxy, with its hundreds of billions of stars, pales in comparison to the luminosity of a single quasar. This immense power is a direct result of the supermassive black hole at its core. These black holes can have masses ranging from millions to billions of times that of our Sun. The energy released as matter falls into the black hole is so immense that it can outshine the combined light of all the stars in the host galaxy. Quasars played a crucial role in the early universe, acting as cosmic lighthouses that illuminated the surrounding darkness. Their intense radiation ionized the intergalactic medium, contributing to the reionization of the universe after the cosmic dark ages. This process was vital for the formation of the first galaxies and stars. Quasars also influenced galaxy evolution by regulating star formation. The energy and radiation they emit can heat up and disperse the gas within a galaxy, preventing it from collapsing to form new stars. This feedback mechanism helps shape the structure and evolution of galaxies over time. The study of quasars provides valuable insights into the early universe and the growth of supermassive black holes. By observing quasars at different distances, astronomers can look back in time, as the light from distant quasars has traveled billions of years to reach us. This allows scientists to study the conditions and processes that prevailed in the early universe. Quasars also serve as probes for studying the intergalactic medium and the large-scale structure of the universe. Their immense power and luminosity make them invaluable tools for exploring the cosmos and unraveling the mysteries of galaxy formation and evolution. Active galactic nuclei, powerhouses of the cosmos. At the heart of some galaxies, a remarkable phenomenon unfolds: active galactic nuclei, AGN. These are not merely centers of galaxies, but colossal engines of energy, driven by supermassive black holes. The scale of these powerhouses is staggering. A single AGN can outshine entire galaxies, emitting energy equivalent to billions of stars. To put this into perspective, consider the Sun, our relatively modest star. If an AGN were to replace the Sun, it would be so luminous that it would cast shadows on Pluto, a distance of about 3.7 billion miles. This immense power originates from the accretion disk of supermassive black holes, where gas and dust spiral inwards at relativistic speeds, releasing enormous amounts of energy in the process. AGNs play a pivotal role in galaxy formation and evolution. They act as cosmic regulators, influencing the growth and structure of their host galaxies. The energy and radiation emitted by AGNs can heat and expel gas, thereby regulating star formation. This process is crucial in determining the size and shape of galaxies. Without AGNs, galaxies might become too large or too small, and their structures could be vastly different. For instance, the Milky Way's supermassive black hole, Sagittarius A*, is relatively quiet compared to AGNs in other galaxies. This quiescence has allowed our galaxy to form stars at a steady pace, leading to the diverse and complex structure we observe today. The power of AGNs is not limited to their host galaxies. They can also influence their surroundings on a much larger scale. AGNs emit powerful jets of plasma that can extend for thousands of light years, interacting with the intergalactic medium. These jets can heat and stir the gas in galaxy clusters, preventing it from cooling and forming stars. This process, known as AGN feedback, is a critical factor in shaping the large-scale structure of the universe. It helps to maintain the balance between star formation and gas consumption, ensuring that galaxies do not exhaust their gas reserves too quickly. In this way, AGNs act as cosmic engines, driving the evolution of galaxies and the universe as a whole. The study of AGNs has revealed a complex and dynamic relationship between supermassive black holes and their host galaxies. This relationship is governed by the principles of astrophysics, but it also holds profound implications for our understanding of the universe. AGNs are not merely passive observers of galaxy evolution. They are active participants, shaping the cosmos in ways that we are only beginning to understand. As we continue to explore these cosmic powerhouses, we gain insights into the fundamental processes that govern the universe, from the smallest scales to the largest. Black holes and galaxy evolution. At the heart of nearly every galaxy, including our own Milky Way, lies a supermassive black hole, a cosmic titan with a mass ranging from millions to billions of times that of our Sun. These celestial behemoths are not merely passive bystanders in the grand theater of the universe. They are dynamic participants, shaping the very galaxies in which they reside. Their immense gravitational pull and energy output influence the formation and evolution of galaxies in profound ways, acting as engines that drive the cosmic machinery. Consider the Milky Way's supermassive black hole, Sagittarius A*, which, despite its massive size, is relatively quiet compared to its more active counterparts in other galaxies. Yet, even in its quiescent state, it exerts a significant influence on the stars and gas in its vicinity. The gravitational pull of supermassive black holes can stir up the interstellar medium, triggering the collapse of gas clouds and sparking the birth of new stars. This process, known as black hole feedback, is a delicate balance between creation and destruction, as the same gravitational forces that nurture star formation can also disrupt it, creating a dynamic and ever-changing galactic ecosystem. In some galaxies, supermassive black holes become active galactic nuclei, AGN, devouring vast amounts of matter and releasing enormous energy in the form of radiation and relativistic jets. These energetic outbursts can have a profound impact on the host galaxy, heating and expelling gas, thereby regulating star formation and shaping the galaxy's morphology. For instance, in elliptical galaxies, the intense energy output from AGN can halt star formation entirely, leading to a population of old, red stars and a galaxy that appears dead in terms of new star birth. In contrast, in spiral galaxies like the Milky Way, the influence of the supermassive black hole is more subtle, allowing for ongoing star formation and a more diverse stellar population. The relationship between supermassive black holes and their host galaxies is symbiotic and complex. As galaxies merge and evolve, so too do their central black holes, growing in mass and influence. This coevolution is evident in the tight correlation between the mass of a supermassive black hole and the velocity dispersion of the stars in its host galaxy's bulge, known as the M-sigma relation. This relationship suggests that the growth of supermassive black holes and their host galaxies are intimately linked, with each influencing the other's evolution. In this cosmic dance, supermassive black holes are not merely passive participants, but active drivers of galaxy formation and evolution, shaping the universe as we know it. The role of supermassive black holes in star formation. At the heart of nearly every galaxy, including our own Milky Way, lies a supermassive black hole, a cosmic titan with a mass ranging from millions to billions of times that of our Sun. These celestial behemoths are not merely passive bystanders in the grand theater of the universe. They are dynamic participants, shaping the very fabric of their host galaxies. Their immense gravitational pull and energetic processes influence the formation and evolution of stars, making them crucial players in the cosmic dance of creation and destruction. Consider the Milky Way's supermassive black hole, Sagittarius A*, which, while relatively quiet today, has likely played a significant role in the galaxy's star formation history. When active, these black holes can devour vast amounts of matter, releasing enormous energy in the form of radiation and jets of plasma. This energy can heat and disrupt the surrounding gas, potentially stifling star formation. Conversely, in some scenarios, the turbulence generated by these outbursts can trigger the collapse of gas clouds, sparking new waves of starbirth. It's a delicate balance, a cosmic seesaw between creation and suppression. In some galaxies, supermassive black holes are surrounded by dense, donut-shaped structures known as torus. These structures are rich in gas and dust, providing ample fuel for the black hole and a nursery for star formation. The intense radiation from the black hole can compress the gas in the torus, leading to the birth of new stars. This process is not uniform, however. The same radiation that triggers star formation can also evaporate the gas, creating a complex interplay of forces that governs the rate and scale of star formation. The influence of supermassive black holes extends far beyond their immediate vicinity. Their gravitational pull can shape the orbits of stars and gas clouds, funneling material into the galactic center and fueling bursts of star formation. In some cases, they can even trigger the formation of entire clusters of stars. For instance, the Arches cluster near the Milky Way center is a testament to this process, containing some of the youngest and most massive stars in our galaxy. Thus, supermassive black holes are not just cosmic vacuum cleaners. They are engines of the universe, driving the formation and evolution of stars and galaxies. Gravitational waves, ripples in spacetime. Gravitational waves, often described as ripples in the fabric of spacetime, are among the most profound predictions of Einstein's theory of general relativity. These waves are generated by the acceleration of massive objects, such as orbiting black holes or neutron stars. The sheer scale of supermassive black holes, which can be millions or even billions of times more massive than our Sun, makes their gravitational waves particularly powerful. When two such behemoths spiral toward each other, the resulting gravitational waves can distort space-time itself, creating ripples that travel across the universe at the speed of light. These waves carry with them information about the cataclysmic events that produced them, offering astronomers a new way to observe the cosmos. The detection of gravitational waves from supermassive black holes is a monumental challenge due to their incredibly long wavelengths. Unlike the waves detected by observatories like LIGO, which originate from smaller black holes, those from supermassive black holes have wavelengths that can span light years. This means that detecting them requires a detector of similar scale. Scientists are exploring various methods to achieve this, including using arrays of pulsars or future space-based interferometers. The successful detection of these waves would provide unprecedented insights into the dynamics of galaxy formation and evolution. For instance, the merger of two supermassive black holes can release an enormous amount of energy, influencing the shape and structure of the galaxies they inhabit. Supermassive black holes play a pivotal role in shaping the galaxies around them. Their immense gravitational pull can influence the orbits of stars and gas clouds, driving the formation of new stars and even triggering violent outbursts of energy. When these black holes merge, the resulting gravitational waves can carry away a significant amount of energy, causing the black holes to recoil and potentially eject them from their host galaxies. This process can have profound implications for the evolution of galaxies, as the loss of a central supermassive black hole can disrupt the delicate balance of forces that maintain galactic structure. Understanding these dynamics is crucial for unraveling the mysteries of the universe's largest structures. The study of gravitational waves from supermassive black holes is not just about detecting these elusive ripples in spacetime. It's about unlocking the secrets of the cosmos. By observing these waves, scientists can probe the very fabric of spacetime, testing the limits of Einstein's theory and exploring the nature of gravity itself. The information carried by gravitational waves can reveal the properties of black holes, their spin, and their masses, providing a wealth of data that optical telescopes cannot. This multidisciplinary approach, combining theoretical physics, observational astronomy, and advanced technology, promises to revolutionize our understanding of the universe. The journey to detect these waves is ongoing, but the potential rewards are immense, offering a glimpse into the most powerful and enigmatic phenomena in the cosmos: the mystery of black hole mergers. In the vast cosmic ballet, supermassive black holes take center stage, their immense gravity orchestrating the dance of galaxies. These celestial titans, millions to billions of times more massive than our Sun, lurk at the hearts of galaxies, their presence betrayed only by the violent swirl of matter around them. Their influence is profound, shaping the very fabric of their host galaxies. Yet, their most enigmatic behavior lies in their mergers, events so cataclysmic they ripple the fabric of spacetime itself. Picture two supermassive black holes, each anchored in its own galaxy, drawn together by the inexorable pull of gravity. As their galaxies collide and merge, so too do the black holes, spiraling inward in a cosmic waltz that lasts millions of years. The final stages of this dance are a violent crescendo, a collision that releases a torrent of energy, warping spacetime and sending gravitational waves rippling across the universe. These waves, predicted by Einstein a century ago, were finally detected in 2015, opening a new window into the universe's most extreme phenomena. The power unleashed in these mergers is staggering. In a single instant, a black hole merger can emit more energy than all the stars in the universe combined. This energy stirs up the surrounding gas and dust, triggering bursts of star formation and reshaping the galaxy. It's a dramatic reminder of the black hole's role as an engine of galactic evolution. Yet, despite their profound influence, these mergers remain shrouded in mystery. Astronomers are still unraveling the details of these cosmic clashes, their work guided by the faint whispers of gravitational waves and the violent outbursts of light that echo across the universe. One of the most intriguing aspects of black hole mergers is their rarity. Despite the vastness of the universe, these events are fleeting, their signals detectable only by the most sensitive instruments. Yet, each detection offers a treasure trove of data, a glimpse into the physics of the extreme. For instance, the first detected black hole merger, GW150914, revealed black holes more massive than any previously observed. This challenged existing models of black hole formation and evolution, sparking a flurry of research. As gravitational wave astronomy advances, more such discoveries are expected, each one a piece in the puzzle of black hole mergers. Supermassive black holes and dark matter. At the heart of nearly every galaxy, including our own Milky Way, lies a supermassive black hole, an object so dense and massive that its gravitational pull is incomprehensible. These cosmic behemoths can weigh millions or even billions of times more than our Sun. To put that into perspective, if you replace the Sun with a supermassive black hole of similar mass, the Earth's orbit would remain largely unchanged. Yet, the space within our solar system would become a much darker, colder place. Supermassive black holes are the engines that drive galaxy formation and evolution. They shape the cosmos through their immense gravitational influence and the energetic processes that occur in their vicinity. Their presence can influence the orbits of stars, the formation of new stars, and even the distribution of dark matter, the mysterious, invisible substance that makes up about 27% of the universe's total mass and energy content. Dark matter, though invisible, exerts a gravitational force that binds galaxies together and influences their rotation. It's like an invisible scaffolding that holds the visible universe in place. Supermassive black holes interact with this dark matter, creating a complex dance of gravity and motion. As galaxies collide and merge, their supermassive black holes can merge too, releasing a tremendous amount of energy in the form of gravitational waves. These waves ripple through the fabric of space-time, potentially leaving imprints on the distribution of dark matter. The interplay between supermassive black holes and dark matter is a crucial factor in understanding the large-scale structure and evolution of the universe. It's a cosmic ballet that plays out over billions of years, shaping the galaxies we see today. The relationship between supermassive black holes and dark matter is still a topic of ongoing research. Scientists are using sophisticated computer simulations and advanced observational techniques to unravel the mysteries of these cosmic powerhouses. For instance, the Event Horizon telescope, a global network of radio observatories, has captured the first-ever image of a black hole shadow, providing valuable insights into these enigmatic objects. Meanwhile, experiments like the Large Hadron Collider and the Dark Energy Survey are probing the nature of dark matter, hoping to shed light on its properties and interactions. The more we learn about supermassive black holes and dark matter, the better we understand the fundamental forces that govern our universe. It's a journey of discovery that continues to push the boundaries of human knowledge and imagination. The Event Horizon Telescope, capturing the unseeable. At the heart of every major galaxy lies a supermassive black hole, a cosmic leviathan whose gravitational pull shapes the very fabric of its surroundings. These celestial giants are not merely voids of darkness, but engines of creation, driving the formation and evolution of galaxies. Their immense scale is almost incomprehensible. A single supermassive black hole can be millions or even billions of times more massive than our Sun. To put that into perspective, if our Sun were a grain of sand, a supermassive black hole would be a boulder the size of a small mountain. Their power is equally staggering, capable of bending light, warping space-time, and spewing out jets of energy that can stretch for thousands of light years. Capturing an image of these elusive behemoths is a challenge that pushes the boundaries of technology and human ingenuity. Enter the Event Horizon Telescope, EHT, a global network of radio observatories that work in unison to achieve an angular resolution so fine, it's akin to spotting a golf ball on the moon. The EHT doesn't just observe black holes. It peers into the abyss, capturing the unseeable by detecting the silhouette of a black hole against the backdrop of the glowing, superheated material that surrounds it. This is no easy feat. The data collected is so vast that it can't be transmitted electronically. Instead, it's shipped on physical hard drives to a central location for processing. The EHT's first target was the supermassive black hole at the center of the galaxy M87, some 55 million light-years away. The resulting image, released in 2019, was a groundbreaking achievement, revealing a dark central region, or shadow, surrounded by a bright ring of light. This ring is the accretion disk, a swirling maelstrom of gas and dust heated to billions of degrees as it spirals inwards, inevitably consumed by the black hole's insatiable appetite. The image provided the first direct visual evidence of the shadow of a black hole, a phenomenon predicted by Einstein's theory of general relativity. It's a testament to human curiosity and technological prowess, a glimpse into the very heart of the universe. The EHT's work is far from over. Future observations promise to delve even deeper, capturing images of other supermassive black holes, including the one at the center of our own Milky Way galaxy, Sagittarius A star. Each image is a piece of a cosmic puzzle, a snapshot of the engines that power the universe. By studying these images, scientists hope to unravel the mysteries of black holes, from their formation and growth to their role in shaping galaxies and the cosmos as a whole. The EHT is more than a telescope. It's a window into the unseen, a tool that allows us to stare into the abyss and, perhaps, understand the very nature of reality, simulating the unsimulatable. Supermassive black holes, those cosmic behemoths lurking at the hearts of galaxies, are a testament to the universe's penchant for extremes. These objects, with masses ranging from millions to billions of times that of our Sun, exert a gravitational pull so immense that not even light can escape their grasp. Their influence extends far beyond their event horizons, shaping the very fabric of their host galaxies. Picture a city the size of the Milky Way, with a black hole at its center that's as heavy as a small galaxy. This isn't science fiction, it's the reality of supermassive black holes. Their role in galaxy formation and evolution is nothing short of monumental. They act as cosmic engines, driving the evolution of galaxies through processes like accretion and feedback. As matter spirals into a supermassive black hole, it forms an accretion disk, a swirling maelstrom of gas and dust that heats up to incredible temperatures, emitting intense radiation. This radiation can influence star formation, either by triggering it or by quenching it, depending on the circumstances. It's like a cosmic thermostat, regulating the temperature and activity of the galactic environment. Simulating these processes is a daunting task. The scales involved are staggering, from the subatomic particles in the accretion disk to the galactic structures spanning thousands of light years. Current computational resources, while impressive, often fall short of capturing the full complexity of these systems. Scientists employ various approximations and simplifications, focusing on specific aspects of the problem. For instance, they might simulate the dynamics of the accretion disk in detail, while treating the rest of the galaxy as a simpler, less detailed model. This approach, known as multi-scale modeling, allows researchers to tackle different aspects of the problem separately. Despite these challenges, simulations have provided valuable insights. They've shown how supermassive black holes can influence the distribution of dark matter in galaxies, how they can trigger star formation in some regions while quenching it in others, and how they can drive powerful jets of plasma that extend far beyond the galaxy itself. These simulations are not just about understanding the past, they're about predicting the future. By modeling the behavior of supermassive black holes, scientists can make predictions about the evolution of galaxies, the large-scale structure of the universe, and even the nature of black holes themselves. It's a complex, ongoing endeavor, but one that promises to deepen our understanding of the cosmos. Black holes and the multiverse. Supermassive black holes, those cosmic behemoths lurking at the hearts of galaxies, wield power that shapes the very fabric of the universe. Their immense gravity, millions or even billions of times that of our Sun, bends space-time itself. Picture a pebble dropped into a pond, the ripples spreading outwards. Now, imagine that pebble as a supermassive black hole and the pond as the universe. The ripples, in this case, are the gravitational waves that warp the cosmos, influencing the formation and evolution of galaxies. These celestial giants are not just passive observers, they actively participate in the cosmic dance. They devour surrounding matter, releasing enormous energy in the process. This energy can heat and expel gas from galaxies, regulating star formation. It's a cosmic balancing act, where supermassive black holes prevent galaxies from growing too quickly, thus influencing their size, shape, and structure. Without these cosmic engines, galaxies might look vastly different, if they could form at all. The role of supermassive black holes extends beyond their immediate surroundings. They may even play a part in the multiverse, a hypothetical set of possible universes. Some theories suggest that our universe might have been born from a black hole in a parent universe. This idea, known as the black hole cosmology correspondence, proposes that black holes could be gateways to other universes. While this remains speculative, it's a fascinating thought that these cosmic engines might be the architects of the multiverse, seeding new universes from their gravitational wombs. Moreover, supermassive black holes could be the key to understanding the fundamental nature of reality. Their extreme conditions challenge our understanding of physics, pushing the boundaries of what we know. By studying these cosmic titans, we might unlock secrets about the fabric of space-time, the nature of gravity, and the ultimate fate of the universe. In this sense, supermassive black holes are not just engines of the universe. They are also the keys to unlocking its deepest mysteries. The information paradox. What happens to information? Supermassive black holes, those cosmic behemoths lurking at the hearts of galaxies, wield power beyond human comprehension. They are not just passive giants. They actively shape their surroundings, influencing the very fabric of galaxies. Picture a city where a single entity controls the flow of traffic, the distribution of resources, and even the weather. That's a supermassive black hole in a galaxy. It regulates star formation, gas dynamics, and even the overall structure of the galaxy. Their immense gravitational pull can accrete matter, forming an accretion disk that emits intense radiation, outshining entire galaxies. This process, known as active galactic nuclei, AGN, can release energy equivalent to billions of stars, making them the most powerful engines in the universe. Now, let's dive into the enigmatic world of the information paradox. When matter falls into a black hole, it's not just lost, it's scrambled. The information about its state, its history, its very essence, seems to vanish. This is a problem because, according to the laws of physics, information can't just disappear. It's like burning a book. The ashes remain, but the story is gone. Or is it? The paradox arises because black holes eventually evaporate, releasing energy in the form of Hawking radiation. But this radiation is random and carries no information about the matter that formed the black hole. So, what happens to the information? Does it leak out in some way we haven't detected yet? Or is it stored in the black hole's entropy, waiting to be decoded? These questions challenge our understanding of quantum mechanics and general relativity. The scale of supermassive black holes is equally mind-boggling. They can be millions or even billions of times more massive than our sun. To put that into perspective, if our sun were a grain of sand, a supermassive black hole would be a small boulder. Their event horizons, the points of no return, can span millions of miles. Yet, despite their size, they are incredibly dense. A supermassive black hole's density is so high that if you could somehow compress Earth into one, it would fit into a marble. This immense density warps space-time, creating a gravitational well so deep that not even light can escape. It's like a cosmic whirlpool, dragging in everything that gets too close. The role of supermassive black holes in galaxy formation and evolution is a hot topic in astrophysics. They seem to co-evolve with their host galaxies, growing in tandem. This suggests a symbiotic relationship where the black hole's activity regulates star formation and vice versa. For instance, the powerful jets emitted by some supermassive black holes can heat and disperse gas, preventing it from forming stars. This feedback mechanism can halt star formation, shaping the galaxy's evolution. It's a delicate balance, a cosmic dance between creation and destruction. Understanding this dance is crucial for unraveling the mysteries of galaxy formation and the universe's large-scale structure. Hawking radiation, black holes are not eternal. Supermassive black holes are cosmic titans, anchoring the centers of galaxies with gravitational pulls so immense they bend space-time itself. These celestial behemoths can be millions or even billions of times more massive than our sun. To put that into perspective, if our sun were the size of a grain of sand, a supermassive black hole would be a boulder. Their power is unparalleled, driving the very formation and evolution of galaxies. They act like cosmic engines, regulating star formation, influencing galactic structure, and even shaping the distribution of dark matter. Without them, galaxies as we know them might not exist. At the heart of every large galaxy, including our own Milky Way, lies a supermassive black hole. These monsters are not just passive bystanders. They actively shape their surroundings. They devour surrounding matter, releasing enormous amounts of energy in the process. This energy can heat and ionize gas, creating spectacular displays like quasars, which are among the brightest objects in the universe. The sheer scale of their influence is staggering. For instance, the supermassive black hole at the center of the galaxy M87 has a mass equivalent to 6.5 billion suns and powers a jet of plasma that stretches for thousands of light years. However, these colossal entities are not eternal. Despite their immense power, black holes are not invincible. They are subject to a process known as Hawking radiation, a theoretical prediction by physicist Stephen Hawking. This phenomenon arises from quantum effects near the event horizon, the point of no return around a black hole. Hawking radiation causes black holes to slowly lose mass over time, eventually leading to their evaporation. For supermassive black holes, this process is incredibly slow. It would take longer than the current age of the universe for even the smallest supermassive black holes to evaporate completely. Yet, it is a reminder that nothing in the cosmos is truly eternal, not even these titans of the universe. The implications of Hawking radiation are profound. It suggests that black holes have a finite lifespan, albeit an extraordinarily long one. This process also raises questions about the ultimate fate of information that falls into a black hole. According to the laws of physics, information cannot be destroyed, but Hawking radiation seems to imply that it might be lost forever. This paradox has puzzled physicists for decades and remains one of the most intriguing open questions in theoretical physics. Despite these uncertainties, the study of Hawking radiation and black holes continues to push the boundaries of our understanding of the universe. The future of black hole research. Supermassive black holes, those cosmic behemoths lurking at the hearts of galaxies, are not just passive monsters. They actively shape their surroundings, influencing the very fabric of the universe. Their immense gravity, millions or even billions of times that of our sun, can dictate the fate of entire galaxies. Picture a cosmic puppet master pulling strings that control the birth and death of stars, the formation of galactic structures, and even the distribution of dark matter. Their influence is so profound that they can trigger star formation or quench it entirely, depending on their mood, so to speak. This is why understanding their behavior is crucial for unraveling the mysteries of galaxy formation and evolution. In the coming decades, black hole research is set to enter an exciting new era. Advances in technology are allowing us to peer deeper into the cosmos than ever before. The Event Horizon telescope, which famously captured the first image of a black hole in 2019, is just the beginning. Future telescopes, both on Earth and in space, will provide even sharper images and more detailed data. These tools will help us study not just the shadows of black holes, but also the swirling disks of hot gas and dust that surround them, known as accretion disks. By analyzing the light and radiation emitted from these disks, scientists hope to unlock the secrets of black hole growth and behavior. Moreover, gravitational wave astronomy is opening up a new window into the universe. These ripples in space-time, caused by massive, accelerating objects, can reveal the mergers of black holes billions of light years away. Each detection is a cosmic symphony, telling us about the masses, spins, and distances of the black holes involved. In the future, we might even detect the gravitational waves from the very formation of supermassive black holes, providing a direct probe into the early universe. This is not just about understanding black holes. It's about understanding the universe itself. Theoretical research is also set to make significant strides. Scientists are developing sophisticated computer models to simulate the complex physics of black holes. These models can help us understand how black holes interact with their surroundings, how they grow, and how they influence galaxy formation. Additionally, researchers are exploring the quantum nature of black holes, delving into the mysteries of Hawking radiation and the information paradox. This is where theoretical physics meets cosmology, and the results could revolutionize our understanding of the universe. The future of black hole research is not just about observing these cosmic giants. It's about unraveling the fundamental laws of nature. Black holes and the search for extraterrestrial life. Supermassive black holes, those cosmic behemoths lurking at the centers of galaxies, wield an influence so profound it shapes the very fabric of the universe. These monsters, millions to billions of times more massive than our Sun, are not just passive bystanders in the cosmic ballet. They actively sculpt galaxies, driving star formation and influencing the distribution of matter on scales spanning thousands of light years. Their immense gravitational pull can trigger the birth of new stars or, conversely, prevent them from forming, all while spewing out energy in the form of quasars and relativistic jets. This dual role as both creators and destroyers makes them pivotal players in the cosmic ecosystem. The search for extraterrestrial life is intrinsically linked to our understanding of these cosmic giants. Life as we know it requires a delicate balance of conditions, a stable environment, access to energy, and the right chemical ingredients. Supermassive black holes, with their ability to regulate galaxy dynamics, indirectly influence these conditions. For instance, their activity can stir up interstellar gas, potentially seeding the galaxy with the raw materials for life. However, their immense power can also be a double-edged sword. Intense radiation and gravitational forces near active supermassive black holes could strip away atmospheres and disrupt planetary systems, making life as we know it challenging to sustain. This paradoxical nature underscores the complex interplay between these cosmic engines and the potential for life to emerge. Moreover, the study of supermassive black holes offers insights into the habitability of galaxies. Galaxies with actively feeding supermassive black holes, known as active galactic nuclei, AGN, can bathe their surroundings in high-energy radiation. This radiation could be detrimental to life, but it might also drive complex chemical reactions that could lead to the formation of organic molecules, the building blocks of life. Understanding these processes is crucial for identifying galaxies that might harbor life-friendly environments. For example, galaxies with supermassive black holes that are dormant or have low activity levels might provide more stable conditions for life to thrive. This nuanced understanding is essential for guiding our search for extraterrestrial life. as it helps us focus on galaxies that are more likely to meet the necessary conditions. In the grand tapestry of the cosmos, supermassive black holes are both architects and disruptors. Their influence extends far beyond their immediate vicinity, shaping the evolution of galaxies and, by extension, the potential for life within them. As we continue to explore the universe, our understanding of these cosmic engines will be instrumental in unraveling the mysteries of extraterrestrial life. From the birth of stars to the formation of planetary systems, the role of supermassive black holes is a testament to the intricate and interconnected nature of the cosmos. Their study not only deepens our knowledge of the universe, but also brings us closer to answering one of humanity's most profound questions: are we alone in the cosmos? The cosmic web, connecting black holes and galaxies. In the vast expanse of the universe, supermassive black holes, SMBHs, sit at the heart of nearly every galaxy, acting as cosmic engines that shape their surroundings. These behemoths, with masses ranging from millions to billions of times that of our Sun, exert an influence far beyond their immediate vicinity. Their immense gravitational pull and energetic processes, such as accretion and jet formation, create a complex web of interactions that connect black holes to their host galaxies and beyond. This cosmic web is not a physical structure, but a dynamic network of energy, matter, and feedback mechanisms that govern galaxy formation and evolution. The scale and power of SMBHs are difficult to comprehend. To put it into perspective, the SMBH at the center of our Milky Way galaxy, known as Sagittarius A*, has a mass of about 4 million suns. If you were to replace the Sun with Sagittarius A*, its event horizon would stretch out to the orbit of Mercury, engulfing our planet in inescapable darkness. Yet, despite their immense size, SMBHs are incredibly dense, with a radius that is often only a few times larger than the event horizon. This density gives them an extraordinary gravitational pull, capable of bending spacetime and accelerating matter to near-light speeds. The energy released during accretion, when matter falls into the black hole, can outshine entire galaxies, making these regions some of the brightest objects in the universe. The cosmic web connecting SMBHs and galaxies is a testament to the intricate balance of creation and destruction. As matter spirals into a black hole, it forms an accretion disk, a swirling maelstrom of superheated gas and dust. The friction and compression in this disk generate enormous amounts of energy, often in the form of tinth rays and other high-energy radiation. This energy can drive powerful winds and jets that extend thousands of light years into space. These outflows can both nurture and stifle star formation, depending on their intensity and the environment. In some cases, they provide the necessary turbulence to trigger the collapse of gas clouds, birthing new stars. In others, they blast away the very material needed for star formation, effectively shutting down the galaxy's ability to create new stars. The influence of SMBHs extends even further, shaping the large-scale structure of the universe. Galaxies are not isolated islands, but are connected by filaments of dark matter and gas, forming a cosmic web that spans hundreds of millions of light years. SMBHs at the centers of these galaxies can influence the flow of matter along these filaments, regulating the supply of gas that fuels star formation. This regulation is crucial for understanding why some galaxies are bustling with star formation while others are quiet and dormant. The feedback from SMBHs helps maintain this balance, ensuring that galaxies do not consume their gas reserves too quickly or too slowly. Without this feedback, the universe would look vastly different, with galaxies either burning out too soon or remaining stagnant, never reaching their full potential. Black holes and the fate of the universe. Supermassive black holes, those cosmic behemoths lurking at the hearts of galaxies, wield an influence so profound it shapes the very fabric of the universe. These monsters, millions to billions of times more massive than our Sun, are not just passive bystanders. They actively sculpt galaxies, driving star formation and even quashing it when they grow too powerful. Their immense gravity bends space-time, creating a cosmic whirlpool that drags in gas, dust, and even stars. This process, known as accretion, releases staggering amounts of energy, outshining entire galaxies in a phenomenon called quasars. It's like a cosmic engine, converting the potential energy of infalling matter into radiation, often outshining entire galaxies. The scale of these engines is hard to fathom. The supermassive black hole at the center of our Milky Way, Sagittarius A*, has a mass of about 4 million suns. Yet, it's relatively small compared to others. Some galaxies host black holes with masses billions of times that of our Sun. To put that into perspective, if you replace the Sun with a black hole of the same mass, the orbits of the planets wouldn't change. But if you replace the Sun with a supermassive black hole from an active galaxy, the solar system would be engulfed within its event horizon. That's the power of scale we're dealing with. These cosmic giants play a crucial role in galaxy evolution. They regulate star formation by heating and blowing away the gas that would otherwise collapse to form new stars. This is known as feedback. Without it, galaxies might burn through their star-forming gas too quickly, leading to a universe filled with red and dead galaxies. But with it, galaxies can sustain star formation over billions of years, leading to the diverse cosmic landscape we see today. It's a delicate balance, a cosmic dance between creation and destruction. Looking to the future, supermassive black holes will continue to shape the universe. As galaxies collide and merge, their central black holes will too, growing ever larger. In the far future, as the universe expands and galaxies drift apart, these mergers will become rarer. The supermassive black holes will slowly consume the remaining gas and stars, growing ever larger but also ever more isolated. In a sense, they will become the last remnants of the galaxies they once ruled, outlasting stars and planets, and perhaps even dark matter. They will be the engines that keep on running, long after the universe has grown cold and dark. The philosophy of black holes, exploring the unknown. Supermassive black holes, those enigmatic giants lurking at the hearts of galaxies, wield an influence so profound it reshapes the very fabric of the cosmos. Their scale is staggering, with masses ranging from millions to billions of times that of our Sun. To grasp their enormity, consider this. If our Sun were a grain of sand, a supermassive black hole would be a mountain. Their gravitational pull is so intense that not even light can escape, making them invisible to our telescopes. Yet, their presence is betrayed by the violent, swirling maelstrom of gas and dust that surround them, emitting intense radiation across the spectrum. These cosmic behemoths are not merely passive observers in the grand theater of the universe. They are active participants, shaping the evolution of galaxies in ways that scientists are still unraveling. One of the most compelling theories suggests that supermassive black holes regulate star formation. As they consume matter, they release enormous amounts of energy, which can heat up and disperse the gas needed for stars to form. This feedback mechanism prevents galaxies from growing too large too quickly, maintaining a delicate balance that allows for the diverse array of galaxies we observe today. In this way, supermassive black holes act as cosmic thermostats, controlling the temperature and density of the interstellar medium. The role of supermassive black holes in galaxy formation is further illustrated by the correlation between their mass and the mass of the galactic bulge. This relationship, known as the M-sigma relation, suggests a coevolutionary path where the growth of the black hole is intricately linked to the growth of the galaxy. As galaxies merge and evolve, so too do their central black holes, growing through accretion and merging with other black holes. This dynamic interplay underscores the interconnectedness of cosmic phenomena, where the fate of one entity is inextricably tied to another. Supermassive black holes, with their immense scale and power, are not just bystanders in the universe's grand narrative. They are active agents, shaping the cosmos in ways that continue to captivate and challenge our understanding of the unknown. The art and science of black hole visualization. Supermassive black holes, those cosmic behemoths lurking at the hearts of galaxies, are not just captivating subjects for science fiction. They are very real, and their immense scale and power shape the very fabric of the universe. These celestial giants can be millions or even billions of times more massive than our Sun. To put that into perspective, if our Sun were the size of a grain of sand, a supermassive black hole could be as large as a basketball. Their gravitational pull is so strong that not even light can escape, making them invisible to the naked eye. Yet, their presence is betrayed by the violent, swirling maelstrom of gas and dust that surround them, known as accretion disks. These disks emit intense radiation, making the regions around black holes some of the brightest objects in the universe. Visualizing these enigmatic objects is a complex task that blends art and science. Scientists use sophisticated computer models to simulate the behavior of matter and energy in the vicinity of a black hole. These simulations take into account the intense gravitational forces, the swirling accretion disks, and the relativistic effects that warp space and time. The results are stunning images that show the warped light and distorted stars near the event horizon, the point of no return for anything drawn into the black hole's grasp. One of the most iconic visualizations is the image of the supermassive black hole at the center of the galaxy M87, captured by the Event Horizon telescope. This groundbreaking image, released in 2019, shows a glowing ring of light surrounding a dark central region, providing the first direct visual evidence of a black hole. The role of supermassive black holes in galaxy formation and evolution is a hot topic in astrophysics. They are thought to influence the growth and structure of galaxies through a process known as feedback. As matter falls into a black hole, it releases enormous amounts of energy, which can heat the surrounding gas and prevent it from cooling and forming stars. This regulatory mechanism helps control the rate of star formation and can even halt it altogether, shaping the overall structure and evolution of the galaxy. For instance, in the Milky Way, the supermassive black hole at its center, Sagittarius A*, is relatively quiet, allowing star formation to proceed at a steady pace. In contrast, in some galaxies, the black hole's activity is so intense that it can quench star formation entirely, leading to the formation of red and dead galaxies that are devoid of young, hot stars. Understanding the art and science of black hole visualization is not just about creating stunning images. It's about unraveling the mysteries of the universe and our place within it. By studying these cosmic giants, scientists hope to gain insights into the fundamental laws of physics, the nature of space-time, and the origins of galaxies. The visualization of black holes is a testament to human ingenuity and our relentless quest for knowledge. It bridges the gap between the abstract and the tangible, bringing us face to face with the most extreme and enigmatic objects in the cosmos. As we've journeyed through the cosmos, we've seen that supermassive black holes are not the cosmic vacuum cleaners of popular myth, but rather the grand conductors of the universe's symphony. These titans, millions to billions of times the mass of our Sun, reside at the hearts of galaxies, shaping their formation and evolution. Imagine, if you will, our own Milky Way. At its center, a supermassive black hole, for a million times the Sun's mass, spins and feeds, influencing the very fabric of our galaxy. It's like the universe's ultimate traffic cop, directing the flow of stars and gas, sparking star formation, and even influencing the very structure of galaxies. We've learned that these cosmic behemoths are born with their galaxies, growing and evolving together. They're not just passive observers, but active participants in the cosmic dance. They heat and cool galaxies, trigger star formation, and even blow powerful winds that can sweep entire galaxies clean of the gas needed to form new stars. It's a delicate balance, a cosmic seesaw of creation and destruction. So what's next? Well, we're just scratching the surface. There's still so much to learn about these enigmatic objects. How do they form? How do they influence their host galaxies? And what can they tell us about the very fabric of the universe? Join us in the next episode as we continue to unravel the mysteries of the cosmos. Until then, keep looking up, keep wondering, and remember, the universe is not just out there. It's within us, guiding our journey, just as these supermassive black holes guide the dance of the cosmos.